model of Electroweak interactions. These lectures will be very, very basics. But anyway, if you have questions, you can ask the organizers or the lecturer or the tutor. So, can I start? I can start? Yeah, okay. Good. So, we will talk about the unified field theory of electromagnetic and weak interactions, and I will assume you all know a number of things, which is essentially our basic language. First thing I will assume you know is that we speak the language of field theory. Relativistic quantum mechanics is done in the context of field theory. And I assume that you all know that within field theories, an important role is played by invariance properties. Actually, invariance properties, symmetry properties of the theory of the Lagrangian density, essentially define the field theory itself. I will also assume you all know more or less what perturbative renormalizability means. But I will say something about that, so that will not be assumed completely. We will heavily use the idea of gauge invariance in particular. Gauge invariance is known to everybody from QED, from electromagnetism, and then the idea of gauge invariance was extended to non-abelian invariance groups by Young and Mills around in the 50s, and this will be our guideline in the construction of the unified model of electroweak interactions. And finally, I will assume you know what perturbative covariant perturbative theory is, the language of Feynman diagrams in order to compute decay rates and cross sections. If you are unfamiliar with any of these subjects, well, of course, we will not have time to cover all of them, but we can discuss them in the afternoon or in the tutoring sessions. So, I think you all know what electromagnetism is. So let me say something about basic facts in weak interactions. First, processes which were observed and recognized not to be determined by electromagnetic interaction are beta decay. Beta decay of nuclei is the decay of a nucleus with charge Z and atomic number A into another nucleus with charge Z plus 1 and the same atomic number A, with the emission of an electron. And it was soon recognized that this is not enough. The emission of beta electrons is accompanied by the emission of an anti-neutrino, and we will learn soon that neutrinos come in three different types, three different flavors, and this particular neutrino is called an electron neutrino. And a second process which was early discovered in weak interaction is the decay of the muon. Muons are present in cosmic rays, and they are known to decay into an electron. This minus sign is for the electric charges, you know, with the emission of, which is accompanied by a muon neutrino and by a electron anti-neutrino. These processes are new in the sense they are not strong interactions process nor electromagnetic interaction processes. You need to introduce a new kind of interaction, the weak interactions, in order to explain their existence. So the earlier attempt to a field theory of weak interactions were made by Fermi, as you all know, and Fermi did the naive thing. He just observed that these two processes involve 4 different fermion fields, 4 different spin 1/2 particles, and he wrote a Lagrangian density for these kind of processes, which is essentially the product of 4 Dirac fields, or 4 fermion fields, combined in such a way as to be a Lorentz invariant interaction term. The interaction term of the Lagrangian, of the Fermi Lagrangian, is something like, I will be more precise in a while. There is a constant times a Lorentz invariant combination of 4 Fermi fields, and I will say in a moment what these capital gamma and capital gamma prime are. This constant here was soon recognized to be of the order of 10 to minus 5 times the proton mass to the power minus 2. Each fermion field carry a mass dimension of 3/2, and the Lagrangian density is a quantity with mass dimension 4 in the units in which the Planck constant and the velocity of light are taken to be dimensionless. So 3/2 times 4 makes 6. You need a constant with the dimension of an inverse square mass. I mean, this is an important point. We will see in a moment why. Okay, so it was soon clear that weak interaction do not commute, to use the language of quantum mechanics, with the parity inversion operator. Parity is not conserved by weak interactions, which means that weak interactions distinguish left from right in a maximal way. There is a very long and interesting story of the experiments that led early experimentalists to this conclusion. I will not go through it. Anyway, the precise form of the Fermi Lagrangian, and in particular of these two 4x4 matrices which appear here, is completely determined by the observation that parity is not conserved in weak interactions. And the final form of the Lagrangian density, let me copy it in order not to miss any factor of 2, is something like this. Constant which is traditionally defined with a root of 2 in the denominator, don't ask me why. And then there is a product of 2 currents. You'll see in a minute why I call them currents. You need a creation operator for the proton, so you need a psi bar for the proton field, times the combination gamma mu times 1 plus a constant gamma 5, and the presence of this gamma 5 is what signals violation of the parity operator, times a Dirac field which contains the distraction operator for a neutron, and the rest of the Lagrangian is given by psi bar. We need to create an electron, so sorry, this is an n, not a mu. Psi bar gamma mu 1 minus gamma 5 times an operator which contains the creation operator for antineutrinos, which is psi. Okay, this constant A is there because of reasons which are not of our concern at the moment, but it is rather close to 1 actually. And that's it. And it is a useful, obviously there is another term in the Fermi Lagrangian, which is the one which describes the decay of the muon. The term describing the decay of the muon is something like minus G Fermi divided by root of 2. We need to destroy an electron, psi bar E, gamma mu 1 minus gamma 5, times the distraction operator for the muon. I put it in brackets to distinguish it from the index, times sorry, this is wrong. And then I have to create an electron, psi bar E, gamma mu 1 minus gamma 5 psi nu e. And these operators 1 minus gamma 5, as you probably know, have the role of projecting the Dirac field onto their left-handed components, and the left chirality fermion fields describing the massless limit left-handed, left helicity states, physical states. So it's an interesting exercise to compute the lifetime of a neutron and the lifetime of a muon given this Lagrangian density, and to observe that given the measured values for these two lifetimes, the lifetime of the neutron is around 15 minutes, while the lifetime, this neutron, the lifetime of the muon is around, I don't know, 10 to minus 6 seconds, something like that. I didn't write it down, but something like that. These are very different from each other. But the point is that the phase spaces involved in these two processes are also very different, and the same value of the coupling constant here signals the fact that both processes are governed by the same kind of interactions. We will probably figure out how to compute these quantities in the tutoring lectures. Anyway, so the Fermi Lagrangian describes correctly these two processes, and we could be happy with that were it not for a couple of observations, and this is also something we can discuss during the tutoring lecture in more detail. Point is the following. The Fermi theory of weak interactions is not a renormalizable theory. Renormalization is a complicated subject. I will not go through it. Anyway, there is a simple criteria, necessary criterion, to decide whether a field theory, a field interaction term in the Lagrangian density gives rise to a renormalizable perturbation theory. And the criteria is to count the dimension of the field operator. If the dimension of the field operator appeared in the interaction term exceeds 4, the dimension of space-time, then the theory is not renormalizable. So only dimensionless or couplings with dimension of positive power of an energy, of a mass, are allowed to appear in a renormalizable theory. Here the coupling constant is not has the dimension of an inverse square mass, so the theory is not renormalizable, and perturbation, which means that perturbation theory, it is not possible to use perturbation theory beyond leading order. This is an effective theory. You will have lectures on the subject of effective field theories during this same week, and this is appropriate because the Fermi theory is the first and most known example of an effective field theory, which means a field theory which is valid only up to a given value of the energy involved in the process you are considering. Why am I talking about energy? I'm talking about energy because non-renormalizability of the Fermi theory is closely related to non-unitarity of the Fermi theory of weak interaction. Non-unitarity is what was first observed, I think, historically. And this means that if you know that the scattering matrix in any field, in any acceptable field theory must be unitary, must be a unitary matrix. The S matrix is a matrix which connects in and out states in the scattering theory, and in and out states are two different bases on the same Hilbert space of states. So the connection matrix must be a unitary matrix. And the constraint of unitarity, which is, as you know from basic quantum mechanics, amounts to the constraint of conservation of probability, so it is a very basic thing, is violated by the Fermi theory. It is, well, roughly speaking, the reason is again related to the dimension of the coupling constant. Since there are 2 powers of a mass in the denominator, you have to compensate for that with some power of kinematical invariance, and that amounts to the fact that some cross-section grow with energy, and if you go to sufficiently high energies, you will end up with amplitudes which violate the constraint of perturbative unitarity. So the Fermi theory is an effective theory, which means that it works perfectly well as far as you are concerned with processes at sufficiently low energies, but at some value of the energy, we will see which values of the energy, it is bound to fail at some point. So we would like, for both conceptual and phenomenological reasons, to have a renormalizable and unitary theory of weak interactions. So this is the idea which is at the basis of the birth of the unified theory of electroweak interactions. At the time when weak interactions were discovered and first studied, an example of a renormalizable theory was already at hand, which was QED. In QED, you do not have any interaction vertex with 4 fermions insisting on the same vertex, but you do have 4 fermion interactions, except that they are mediated by the exchange of a vector boson. I guess you are all familiar with this kind of diagrams. It is customary to use solid lines for fermions and wavy lines for vector bosons, and the vector bosons which is involved, which is relevant in QCD, is the photon, of course. You may have even diagrams like this. So in QED, which is a renormalizable field theory, 4 fermion interactions arise from the exchange of vector bosons, of a vector boson. So it was very soon recognized that something like that must be done in order to transform the Fermi theory into a renormalizable theory of weak interactions. However, it was also very soon recognized that while the photon is a massless particle, which was at the time and today, even today, recognized as the origin of the fact that electromagnetic interactions are long-range interactions. They can be transmitted at very long distances because of the fact that the photon is massless. The fact that the photon is massless is related to the fact that the static potential goes like 1 over r. But if you look at weak interactions, you recognize that weak interactions are very shortly ranged, and the easy way to see this is that the presence of a propagator like this gives you a factor of E square, where E is the coupling constant appear in each of these vertices, divided by Q square, which is the propagator of a vector boson with 0 mass. Here Q is the momentum transfer, this is P and P prime, outgoing P prime, Q is P minus P prime. While in the case of the Fermi theory, you have a constant here multiplying the spinors connected to the 4 external legs, which means that if you replace this 4 fermion vertex by the diagram with the exchange of an hypothetical vector boson mediating weak interactions, this must be related to a factor like this, a propagator of a massive vector boson, with q square much less than the square of the mass of the vector of the weak vector boson. Let me call it W, as it was done very soon. W stands for weak. And if the vector boson mediating weak interaction is heavy enough, then this propagator can be replaced by a constant with the dimension of an inverse square mass. So by this rough argument, you can infer some estimate of the value you expect the weak vector boson to have. For example, if you take the coupling constant G to be of order 1, you get MW of the order of the inverse root of the Fermi constant, which means 300 GeV. If you, on the other hand, assume for some reason the coupling constant G to be of the same order of the proton charge, which is what we will actually see to be true, then you get a slightly smaller value of the mass of the vector boson, which is around 100 GeV. Anyway, enormous numbers compared to, for example, to the mass of the proton, but the value to which you have actually to compare them is the value of the photon mass, which is 0. So we want to build a theory of weak interactions where weak interactions are mediated by the presence of a vector boson, but this vector boson must be a massive one. This was recognized very, very soon in the history of weak interactions. And this is actually the reason why at first it looked like there was no hope to build a renormalizable field theory for weak interaction, because the Yang-Mills construction which is the construction of field theories with a gauge invariance based on non-abelian invariance groups. This dates back to 1954. Rather write it down. And in the Yang-Mills construction, mass terms are forbidden. Yang-Mills, the gauge invariance, as in QED, gauge invariance forbids masses for the vector bosons. Anyway, let me for the moment ignore this relevant and important problem, and let me go ahead and try to build a field theory of weak interactions which is based on the idea of gauge invariance. Gauge invariant field theories, even in the non-abelian case, were already known to be renormalizable and unitary. So I want to do that, and I will solve at some point the problem of the mass of the weak vector bosons. So in order to build a gauge theory of weak interactions, I have to do two things. First, I have to identify the invariance group, and then I have to assign fermion fields to representations of that gauge invariance group. And I will do both things, starting from the lepton sector. The paper by Steve Weinberg, 1967. Its title is A Theory for Leptons, and he started with the lepton sector, which is easier. We will see that hadrons pose different problems. Anyway, leptons. Let me write down again the Fermi Lagrangian in the lepton sector. This is given by, I just wrote it down, G Fermi over root of 2, mu bar mu gamma alpha 1 minus gamma 5 times mu. Let me change slightly notation. Instead of psi nu, I just write nu. Instead of psi mu, I just write mu. I just use the symbol of the particle for the fermion fields in order to save writing. Times E bar. E bar now stands for the fermion field, the Dirac field, which is related to the electron, times 1 minus gamma 5 mu E. This is the Fermi Lagrangian for mu decay, and this can be written in the following form: minus 4 gf over root of 2, you'll see in a moment the reason of this extra factor of 4, times j mu E, j alpha mu j alpha E Hermitian conjugate, where I have defined j alpha mu to be mu bar mu gamma alpha 1/2 minus 1 minus gamma 5 times mu, and j alpha for the electron is just the same thing, mu bar E gamma alpha 1/2 1 minus gamma 5 E. I have inserted this factor of 1/2 here in order to have a projector. This is a true projector, an operator which is equal to itself when you take its square. So I pay a tax of a factor of 4. Okay, so this is just an identity. I have defined these two objects, but these two objects have now the appearance of a neutral current, of a current which is related to some invariance of the theory. You know that in field theory, when you have an invariance property, then you have a way to construct conserved current which satisfy the continuity relation d mu j mu equal to 0, which corresponds to the conservation of the space integral of the fourth component, of the time component of the current. So, and current related to fermion fields have the following form. For a generic collection of fermion fields in a given representation of the gauge group, of the invariance group, you have a conserved current for each generator of the gauge group. A is an index which labels the generators of the algebra of the gauge group, and for each of them there is a conserved current, and the TA are the generators in the representation of the fermion fields psi. If you are not familiar with this language, we can discuss it in the afternoon or during the tutoring lectures. Anyway, I will assume that you are all familiar with this idea. So my purpose now is to cast these two currents in the form of a neutral current for a gauge invariant theory. And this is easy to do. This can be done in many different ways, but the simplest way, the way which was suggested by Steve Weinberg, and which turned out to be the correct way actually, is the following. Oh, first of all, let me observe that, for example, the electron current can be written like this. You can insert an extra factor of 1/2 1 minus 5 here, because gamma 5 anti-commutes with gamma mu and anti-commutes with the gamma 0, which is hidden in the Dirac conjugation. So in the end, it is multiplied with 1/2 1 minus 1/2 1 minus gamma 5, which gives 1. So these two currents, the two currents appearing in the Fermi Lagrangian, can be written in terms of the left-handed components of the two fermion fields only. This is nu bar left, gamma mu E left. And the same is true for the muon current. So it turns out that only left-handed component of the Fermi fields are relevant for the Fermi interaction, for the interactions described by the Fermi Lagrangian. So, simplest and in the end correct idea is to define a doublet of left-handed fields. Let me call it L. This script L stands for lepton, and this capital L stands for left. And this doublet is formed out of the left-handed component of the electron neutrino and the left-handed component of the electron fermion fields. This is the doublet for the electron family. There is a similar doublet for the muon family, which is formed with the left-handed component of the muon neutrino and the left-handed component of the muon Dirac field. And you will agree with me that this current here can be written like this. L bar for the electron left-handed, gamma mu, a 2 by 2 matrix, which I call tau plus, times the doublet. And tau plus is 0, 0, 0, 1, 0, 0. This is an identity. This is very trivial. This equal sign here is just a consequence of this definition and the definition of tau plus. But if you do that, you have succeeded in casting the current in the form of a neutral current. You see, there is a fermion field, actually a doublet of fermion fields, actually a doublet of left-handed fermion fields. Gamma mu is fine. A matrix, which I am now interpreting as one of the generators of the gauge invariance group I'm looking for, and the same collection of fermions. So this is the simplest idea. I will also have to include the Hermitian conjugate of this Lagrangian term, which means that there will be the Hermitian conjugate of this current, and if you just take the definitions, you easily find out that the Hermitian conjugate of this current can be written like this: tau minus and tau minus is the Hermitian conjugate of tau plus, but tau plus is real, so it is just a transpose matrix 0, 0, 1, 0. How do we go on? Well, you probably remember that the generators of the algebra of a Lie group are closed under the action of under the commutation operators. The commutator of two generators is a linear combination of the generators themselves. So if tau plus and tau minus are to be interpreted as generators of a gauge invariance group, then I will have to assume that there is a third current, which I call J mu 3, which is the current built out of the commutators, the commutator of tau plus, tau minus. And the commutator of tau plus, tau minus is easy to compute. I can do it here. This is what I call tau 3. And tau 3, sorry, yeah, this is what I call tau 3. And tau 3 is 1, 0, 0, minus 1. I'm not going to compute the commutator in front of you because okay, we are not done yet. We have to check that taking the commutator of tau 3 with either tau plus or tau minus, I don't get anything new. If I get something new, I have to include it in the commutator algebra. Otherwise, I'm done. The algebra is closed upon commutators. But now, at this point, you have already recognized this algebra to be the algebra of the group SU2. This is evident if I introduce matrices. This blackboard is too small for my... What can I erase? I can erase something here. I can write tau plus and tau minus in this form, where tau 1 is 0, 1, 1, 0, and tau 2 is 0 minus I, 0. And at this point, you recognize the spin 2 representation of the group SU2, which is the same group as angular momentum. Here, angular momentum is of no concern for us, but the algebra is the same. So what we are saying is we are guessing that the gauge invariance group, which is what we are looking for, is the group SU2, and we call it SU2 left to remind us that this SU2 only has a non-trivial action only on left-handed components of the fermion fields involved. And the three currents which appear as a consequence of SU2 left invariance are the two currents J mu and J mu dagger, plus the current which I called J mu 3. There is a problem, another problem. We always have the problem of the masses of vector bosons, but now a new problem appears. Well, let me, before saying the new, speaking about the new problem, let me tell you something else. So we now have a guess about what the gauge group might be if the Fermi Lagrangian is an effective theory of a renormalizable gauge theory of weak interactions. I have a guess of which irreducible representation is connected to the left-handed fermion fields. The left-handed fermion fields form a doublet, a representation of dimension 2 of SUT, of SU2. In order to complete this picture, I have to say something about the right-handed components of the same fermion fields. And since they do not appear at all in the Fermi Lagrangian, what I'm saying is that the right-handed components of both the neutrino field and the electron field transform trivially under the action of SU2 left. They do not transform at all. They transform according to the trivial representation of SU2 left. Oh, this structure can be replicated. You can form a doublet out of the electron neutrino and the electron, and then assign the right-handed components to singlets, and then you can do the same for the muon. And in principle, you can replicate this structure as many times as you wish. And in fact, we know that there is at least one third generation of leptons. What is the problem I was mentioning? The problem I was mentioning is that what I call J mu, which is the current formed out of tau plus, is what we call the charged current. What do we mean by that? We mean that if you consider it as it is, as a field operator, it contains, let me write it in the original way, nu bar left, gamma mu E left. It contains the destruction operator of an electron, which is a charged particle, and the creation operator of a neutrino, which is a neutral particle. So, as an operator, when it acts on Hilbert space vectors, it changes the charge of the state vector it acts on. It is a charge current, and as far as we know, only charge current are involved in the Fermi theory. Only charge current are involved in the low energy weak interaction processes. And of course, the same is true for the Hermitian conjugate current, which amounts to exchanging, to swapping E and mu. But if you look at J mu 3, J mu 3 is L bar left, gamma mu tau 3, L bar, L electron, and if you write it down explicitly in terms of the neutrino and electron fields, you find something like nu bar left, gamma mu, nu left, minus, this minus sign is because of the second entry of tau 3 is negative, E bar left, gamma mu E left. And this is a neutral current. Destruction of an electron, creation of an electron. Destruction of a neutrino, creation of a neutrino. It's a diagonal current. It is what we call a neutral current. And it looks like there is no neutral current in the Fermi Lagrangian, so the builder of the Electroweak theory were puzzled by this problem. They succeeded in building a gauge group which gives you the correct charge currents, but it also gives you a neutral current which doesn't appear to be present in the early phenomenology of weak interactions. Of course, they already knew that, for example, the electromagnetic interactions, the electromagnetic current, it is also a neutral current. It's something like psi bar gamma mu psi, the same psi. So this is a neutral current, and it would be nice if the neutral current generated by the SU2 group were precisely the electromagnetic current, but this is not true, as you easily see. There are two important reasons why this J mu3 cannot be identified with the electromagnetic current. The first one is that it only involves left-handed fermions, while QED is parity conserving. The electromagnetic interactions treat on the same footing left-handed and right-handed components of fermion fields. And also there is a neutrino term, and neutrino terms cannot appear in the electromagnetic current because neutrinos are chargeless. So this is a new thing. This is a new current, a weak current, a genuinely weak current, which doesn't appear to be present in data, but okay. We hold on, we press on and live with it up to the point at which some evidence of the presence of weak neutral currents will be given. Of course, there were attempts in the early days of weak interactions to get rid of this unpleasant neutral current, weak neutral current, and you can do it at the price of introducing heavy degrees of freedom, which is something we are very used to. But this turned out very soon not to be needed, not to be necessary. So we keep this neutral current among the currents of our theory and go on. What do we do? Organizers, should I stop for a while or do I go on? Let me look at the faces in order to figure out. I look at careful faces, so I go on. Okay, so we have a neutral current around, and we will at some point decide what to do with it. So it is at this point that Electroweak unification comes in, because since we have a neutral current in our system of conserved currents originating from our guest gauge invariance, we are tempted to enlarge the gauge group in order to include in the system of conserved currents also the electromagnetic current, which is a neutral current. And how can we do that? Well, the easiest way, again, which turned out to be the correct way, is to enlarge the gauge group in order to have one more generator. And the easiest way is to take the direct product of SU2 times a billion factor of U1. U1 is the group of phase transformation. And the idea is now we had 3 generators for this SU2. We have one more generator for U1. We have now 4 generators for the gauge group, and we can try to see whether we are able to arrange this extra U1 factor of the gauge group in order for the system of currents to include also the electromagnetic current. One would naively assume that this extra factor of U1 is just simply the electromagnetic, the gauge group which gives you electromagnetism, but this is impossible. Let me put a cross on it. You cannot do that. And the reason why you cannot do that is that these two factors of the gauge group must commute with each other. And for example, the two components of the left-handed doublet have different values of the electromagnetic charge. This is neutral and this is charged. So since they are mixed by SU2 transformations, the action of SU2 on that doublet cannot commute with U1 if U1 is the U1 of electromagnetism. So this U1 must be something else, and something else is called weak hypercharge, which is usually denoted by capital Y. And we will see in a moment what this weak hypercharge is. Sorry. So how do we build a gauge invariant theory? The recipe is very well known. You have to replace ordinary derivatives of the fermion fields by covariant derivatives. A covariant derivative is a derivative which transforms in the same way as the field does. And the way to define the covariant derivatives is like this, is the ordinary derivative of the fermion fields. Here there are some convention, minus sign, which is conventional. I, the presence of this coupling constant G, is also a matter of conventions. Let me call TA the three generators of SU2 which are relevant for the representation of fermion psi. And then you have an extra connection term related to the U1 factor of the gauge group. Let me call G prime the relevant coupling constant. I will call B mu the vector boson which is related to U1. And then here I have to put a hypercharged quantum number which is customarily written like this, times psi. And this is a covariant derivative under the assumption that the transformation property of the fermion field psi is e to I g ta alpha a of x exponential of I g prime y divided by 2 times beta of x times psi, where beta of x, alpha 1, alpha 2, alpha 3 are three real functions of the space-time coordinates at which we take the field psi. If you take this definition of the action of the group on the generic fermion field psi, here of course you have to choose the correct generators of the gauge group. For example, TA is equal to the 3 Pauli matrices divided by 2 for doublets, and TA equal to 0 for singlets. Left-handed, yes. You can do it. It's they. Sorry. But they do commute by assumption. They act on different indices on the right-hand side. They do commute, and this is precisely the reason why this y cannot be identified with the electron charge. The way you see that y is proportional to the identity matrix in the representation of TA. Okay, so this is the precise definition of the gauge transformation for a generic field in a generic representation of the gauge group, and this is the covariant derivative, in the sense that d mu psi transforms in the same way as psi. So Lagrangian density is now easy to write down. You start by writing down the Lagrangian density for the free propagation of the fermions we are talking about. So it is I L bar left d slash L bar plus I E bar right d slash E right plus I nu bar right d slash nu right. No masses. For the moment. We will talk about fermion masses in later lectures. And then you replace all ordinary derivatives by covariant derivatives according to the different representations of the gauge group. So what you end up is an interacting Lagrangian. This is a free Lagrangian. It only contains quadratic terms in the fields. But if you replace the ordinary derivative by the covariant derivative, I get interaction terms. And the interacting Lagrangian is the free Lagrangian plus something. And I split the interaction terms into two pieces. The one is related to charged current and the other one is related to neutral currents. Let me write them down explicitly. Charge current. Charge current interaction is the term which is related to generators 1 and 2 of SU2, because they are the two non-diagonal generators. So this is simply given by G L bar left gamma mu tau plus L left times well, actually, okay. Yeah, write it like this. Tau 1 over 2 times W mu 1, where W mu 1 is one of the three real vector fields related to the SU2 factor of the gauge group, plus G L bar left gamma mu tau 2 divided by 2 L left W mu 2. And if you want to go back to our previous notation of tau plus and tau minus, you have tau 1 equal to tau plus tau minus, and tau 2 equal to minus I, tau plus minus tau minus. So this is equal to G L bar left gamma mu tau plus L left times 1/2 W1 mu minus I W2 mu plus the Hermitian conjugate. And what is usually done is to write this as G over root of 2 L bar left gamma mu tau plus L left W mu plus the Hermitian conjugate, where I have defined W mu plus minus equal to 1 over root of 2 W mu 1 minus plus I W mu these two complex combinations of W1 and W2 are two electrically charged vector bosons which are coupled to charged currents. This is the charge current interaction terms. The neutral current has two terms. One which comes from the diagonal generator of SU2, tau 3. So it is G L bar left gamma mu tau 3 L left. And the other one comes from the hypercharge term, which is plus G prime. I'm calling G prime the coupling constant related to factor of U1. I have a hypercharged quantum number for both the left-handed neutrino and the left-handed electron, but then here I have to add terms for the right-handed electron. I'm sorry, I forgot to put here the vector boson W mu 3, and all these terms I'm writing down here are coupled to B mu, which is the vector boson related to U1. Okay, this is the neutral current interaction term. This is rather difficult to interpret. It becomes easier if you simplify notations a little bit. Yes? I don't think so. Yes. I actually don't know why there is this root of 2 in the original Fermi constant. I don't think it's related to this, because the relation between G and G Fermi is quadratic, so we will see in a moment. So I was talking about the possibility of simplifying the look of this neutral current term, and the idea is the following. Let me collect all 4 fermion fields: neutrino left-handed, electron left-handed, electron right-handed, neutrino right-handed, into a single object. And then if I do that, I can write the neutral current interaction term as, let me copy it from here so I don't make mistakes. psi bar, where this psi is this 4 component, is an object which is obtained by putting in the same column 4 different 4 components Dirac fields. Psi bar gamma mu G W mu 3 times T3 plus G prime B mu y divided by 2 psi, and these two objects, T3 and y divided by 2, are two 4x4 matrices. They are diagonal matrices which carry in the main diagonal the relevant values for T3 and B mu corresponding to the different fields. So, for example, T3 is 1/2 minus 1/2 for the doublet and 0, 0 for the two singlets. And Y is a 4x4 matrix with the 4 values of the hypercharged quantum number, actually 3 values, because the 2 components of the left-handed doublet have the same hypercharged quantum number. Then I have Y nu R and Y E R. Excellent. So in this way, the neutral current term is easy and we have already seen that neither the current which is coupled to W mu 3 nor the current which is coupled to B mu can be identified with the electromagnetic current. So the idea here, which was originally suggested by Glashow actually, is to replace B mu and W mu 3 by 2 linear combinations of them. And the linear combination was defined originally to be the following: B mu W mu 3 I introduce 2 new vector fields, neutral real vector fields, A mu and Z mu, and I define them to be linear combinations of B mu and W mu 3. This is an orthogonal transformation. The reason why we better choose an orthogonal transformation will be clear in a moment. In principle, one could even take a generic mixing matrix among the two, but it is convenient to take an orthogonal transformation. I just replace B mu and W mu 3 by these 2 linear combination of A mu and Z mu, and A mu and Z mu are defined by this relation here. And theta W is a new parameter which will have to be fixed on the basis of phenomenology at some point. It's an angle. It's called a weak angle. It is sometimes called the Weinberg angle. But this is actually, it was introduced by Glashow, so he was unfortunate in choosing the initial of weak, which was also the initial of Weinberg. Anyway, I do that. And if I do that, it's very easy. I just replace W mu 3 and B mu by the expressions which correspond to this rotation here. And what I get is psi bar gamma mu G sine theta W T3 plus G prime cosine theta w y divided by 2 psi a mu plus a term which is coupled to the z vector boson psi bar gamma mu g cos theta w t3 minus g prime sine theta w, the matrix of hypercharged quantum numbers psi z mu. I did nothing actually, I just reparameterized the theory by this choice of linear combinations of the two neutral current vector bosons. I end up with this expression for the neutral, two neutral current interaction terms. I would like to keep, well, you have them in your notes, and I have them in my notes. And what I now want to do is to try to see whether I can identify one of these two terms with the electromagnetic interaction term, which I know is mediated by a neutral current. I choose this one because I call it. And if I want this to be a mu times the electromagnetic current, the electromagnetic current is the proton charge times psi gamma mu q psi, where q is a diagonal 4×4 matrix which contains in the main diagonal the values of the electric charges of the different particles in units of the proton charge. So it is minus 0, minus 1, 0, minus 1. So this is true. This first weak interaction term can be identified with the electromagnetic interaction term, and therefore the field, which I call A mu, can be identified with the photon field, provided Q, E times Q, is equal to G sine theta W, sorry, T3 plus G prime cosine theta W y divided by 2. So the question is, if there exists a choice of G, G prime, and theta W such that this identity holds true. And of course there is. I have many parameters around I can play with, so I can force this identity. The easy way to do it is to define G and G prime in such a way that G sine theta W and G prime cosine theta W is equal to the proton charge. If I choose parameters in this way, then that identity becomes simply Q equal T3 plus y divided by 2. And this deserves a frame. It's a very interesting relation. It will apply in different cases. What does it mean? For example, it means that you can solve it for the hypercharge matrix. And from this relation here, you can determine which choice of hypercharged quantum numbers you have to make in order for one of the two weak neutral current terms can be identified with the electromagnetic interaction terms. This means, for example, that the hypercharge of the left-handed doublet is equal to 2 times. For example, if I take the first component, Q is equal to 0, which is the charge of the neutrino, and T3 is equal to 1/2, and this gives you -1 for the hypercharge of the left-handed doublet, and you can check that the same value is obtained if you take the second component. If I take the second component, which is the electron, I have a -1 for the electric charge and a -1/2 for the weak isospin quantum number. -1 plus 1/2 is -1/2, so this is again -1. And then I have hypercharge quantum numbers for the right-handed neutrino, for example. Right-handed neutrino has an hypercharge which is twice its electric charge, which is 0, minus the third component of the weak isospin, which is also 0, because I have assumed the right-handed neutrino to be a singlet under the action of SU3, and this is 0. And finally, the right-handed electron has a hypercharge quantum number which is 2 times -1 minus 0, which is -2. So, with these assignments of the hypercharge quantum number, with this choice of the gauge group and this assignment of the hypercharge quantum numbers, I have succeeded, Weinberg and Glashow have succeeded, in constructing a gauge invariant system of currents which includes the charge current of weak interactions, those which appear in the Fermi Lagrangian, and the electromagnetic current. Again, we have a neutral current, which we will have to discover at some point. Let me just note that the right-handed neutrino has obviously 0 electric charge. It has 0, it transforms trivially under the action of SU2 left, and it has also 0 value of the hypercharge quantum numbers. So it looks like the right-handed neutrino doesn't take place in any sense in the in our construction, so I can just forget about it. It is a free object. It doesn't interact neither weakly nor electromagnetically, so it doesn't exist. Of course, we know that it does exist, but we will talk about that later. Anyway, we will not talk about right-handed neutrinos anymore for a while. What about... So this first current here I can just replace by A mu J mu electromagnetic, provided I have this set of choices. I have nothing to say about the interaction, the weak neutral current interaction term, which is related to the Z boson, except that with this assignment we can write it like this: Z mu J mu Z, where J mu Z can be written using these relations. It is written like this. It's I introduce a new 4x4 matrix QZ, which is given by 1 over cosine theta w sine theta w times T3 minus Q sine square theta w. And I have to measure some weak neutral current effect in order to determine the value of QZ, and in particular the value of cosine theta w, which is the only thing which is unknown in this combination. In particular, well, okay. 10 minutes, very good. Go ahead a little bit. What is missing? A lot of things. I better keep this. I can. These I erase, but they are very important. I have to keep in mind. In order to complete the construction, I have to give the vector bosons their own dynamics. So I have to add to our Lagrangian L equal L0. This is the free Lagrangian for the fermions. Then I have the two interaction terms, neutral current and charge currents. And then I have to add a Yang-Mills term for the 4 vector bosons, and this Yang-Mills term is easy to write down. Is simply minus 1 over 4 B mu nu B mu nu minus 1 over 4 W mu nu A W mu nu A. B mu nu is easy to remember because B mu is the vector field related to an abelian factor of the gauge group, so it is simply the anti-symmetric combination d mu b nu minus d nu b mu, while W mu nu A, as you probably know, has a term which is similar to this one. But there is also a quadratic term in the fields without derivatives, and this is related to the fact that the group is non-abelian. It is written like this: epsilon mu nu rho W nu, sorry, epsilon A B C W mu B W nu C, something like this. Let me check the sign. Yes, like this. And this is important because it gives rise to interactions of the gauge bosons with themselves, which is not the case if you have an abelian gauge group. This is actually all, except that we would like to express this term in terms of, instead of W1, W2, W3, and B, we rather write it in terms of A mu, Z mu, and W mu plus minus. The relation between A mu, Z mu, and B mu and W mu 3 is written there. We also had W mu plus minus equal to 1 over root of 2 W mu 1 minus plus I W mu 2. And it's just a matter of algebra, replacing these definitions, this one and this one, into the Yang-Mills Lagrangian to get the final Lagrangian density for the vector fields. I write it down for you. Just copy it in order to complete the construction. Write it here. There are three quadratic terms, which are the usual ones. Where f mu nu Note that there is a factor of 1 over 4 here, as you know from Maxwell equations, a similar factor of 1 over 4 in the z term, which is also a neutral vector, but the kinetic term involving w mu nu is a factor of 1/2 because it is a charge vector. So in order to have the canonical normalization of the propagator, you have to put a factor of 1/2 here instead of a factor of 1/4. And then you have interaction terms. These interaction terms originate from the fact that part of the gauge group is non-abelian. It's written like this: W mu nu plus W mu minus A nu minus W mu nu minus W plus mu A nu plus F mu nu W plus W minus. This is easy to understand in a sense because G sine theta is simply E, and E is the charge of the W boson. And this simply reflects the fact that the W boson, being electrically charged, is coupled to the photon itself. Then there is a similar term in which G sine theta W is replaced by G cosine theta W, and round brackets are just the same except that you have Z instead of the photon field. These are three linear interaction terms. And then you have a 4-vector interaction term, which is, a bit long to write down. The tensor structure is this one: 2g mu nu g rho sigma minus g mu rho g nu sigma minus g mu sigma g nu rho times a long thing, 1/2 W It's not very interesting. Just for the sake of completeness, we write the whole Lagrangian down. A rho A sigma times sine squared theta W plus Z rho Z sigma cosine square theta W plus 2 A rho Z sigma sine theta W cosine theta W. Round bracket, square bracket. That's it. So, I erased the full Lagrangian, L0, L neutral current, L charge current, L Young-Mills. This is the model for leptons. It includes neutral charge current as in the Fermi theory. It includes electromagnetism as we know it. It also includes weak neutral currents, about which we don't know much as yet. But for the rest, it is what we settled out to have. It is a renormalizable and unitary theory of weak interaction of leptons. It is renormalizable and unitary because gauge field theories are known to be renormalizable and unitary. It can be shown on the general ground. There are many missing points. The first one is how to introduce non-zero values for the weak vector bosons. The second one is how to introduce masses for leptons, at least for charged leptons. And finally, do neutral current exist? So we will have to fill these gaps. And there is a fourth one. How do we extend the theory, this construction, to hadrons, which is an important point. So I think I stop here, and we go on tomorrow with the last point, and then we will attack the problem of masses. Okay. Thank you very much.